Sometimes in nature, you stumble across something that just seems too perfect to have been made without prior planning. Like those carrots that grow to look like little people, or the fact that the Earth is just the right distance from the sun to not freeze or fry. Or the fact that, occasionally, lava can cool into monumental hexagonal structures that look like temples and walkways for titans. But impressive as the basaltic columns like the ones at Giant's Causeway in Northern Ireland are, they aren't really ancient engineering projects. Instead, they're the product of some particularly elegant math and physics. And by understanding them, scientists can tap into our planet's geological history and its engineering potential. The Giant's Causeway is one of the most impressive natural structures on the planet. The UNESCO World Heritage Site is made up of more than 40,000 hexagonal basalt columns that descend down into the sea across roughly 3 kilometers of coastline. For a long time, people struggled to believe that such an impressive landscape could be natural, so they've come up with some pretty fantastical tales to explain how it came to look that way. The most famous story is about an Irish giant called Finn McCool, who built the causeway to get to Scotland to fight a rival giant. And another version of the myth describes how Finn battled storms and built the causeway to reach a Scottish maiden who he loved. However, while both of these make for great fireside tales, geological evidence can provide an even more dramatic origin story. 60 million years ago, the ancient continent of Laurasia started to break apart into what would eventually become North America and Europe, as the North Atlantic Ocean grew between them. This tectonic rifting was caused by cataclysmic volcanic eruptions, which saw lava pouring out over the landscape that now makes up Northern Ireland and Western Scotland. It was a similar situation to what we see in Iceland today, where runny basaltic lava formed rivers and pooled into lakes. The first influx of lava came from at least 6 eruptions, but then there was a pause in volcanic activity. The lava solidified and then weathered into a landscape with low hills and wide valleys that became covered in forests. Eventually, the volcanoes started up again, and this time the lava filled up the valleys, burning away trees and creating a 90-meter deep lava lake. That'd be deep enough to swallow pretty much the whole of the Statue of Liberty, pedestal and all. Over time, the lava lake cooled slowly and evenly into basaltic rock. At some point in the process of cooling, the basalt became sculpted into tens of thousands of hexagonal columns, which have been further exposed and shaped by relentless coastal weathering. The regular hexagonal pattern of columns do seem to be too perfect to be natural, but their shapes are the result of some fairly straightforward math and physics. Most substances take up more space when they're liquid than they do when solid, so when something cools and solidifies, it becomes smaller, contracting in 3 dimensions. If the volume of liquid starts out contained, like in a lava lake contained between valley walls, then it puts tension across the whole volume as it contracts. It's still trying to fill that volume, but it has a lot less stuff to do the actual filling. The first bit to cool is the top surface because it's exposed to the cold air, and it releases tension by cracking, just like the mud cracks that form on a dry lake bed. At first, those stress-relieving microfractures all have random orientations, but before long, these fractures self-organize into regular polygons. And that's where nature gets to show off its favorite shape, the hexagon. In lots of different structural systems, hexagons turn out to be the strongest and most efficient way of packing things together. Their trick lies not in the shapes themselves, but in the joints between them. The sides of all the adjacent hexagons meet at an angle of 120 degrees, which distributes stress equally across an area without shearing. So if mechanical strength is what you're really after, then hexagons really are the bestagons. Once the surface has started to crack hexagonally, then the lower insulated layers follow suit. Just like when you're splitting wood, the split that starts at the top propagates downward as the material breaks, following the path of least resistance. Continue that down through 90 meters of cooling lava lake, and you're left with eerily perfect basalt columns. And sure, if you look long enough, you're bound to find a bunch of not hexagons among them too, caused by small-scale irregularities in the lava or the landscape, but on the whole, the hexagons and their 120-degree angles are going to dominate. However, even though math can explain the geometry, it doesn't tell us about how this process actually happens in real time. We needed experiments. One of the biggest questions we had about these hexagonal clusters was whether the fracturing happened at the moment of solidification, or when the solid basalt was hot, cold, or somewhere in between. So in 2018, scientists from the UK did some experimental research, heating up columns of basalt until they were at their melting point, and watching them solidify again in the hopes of catching the fractures in action. This was the first time something like this had been done by people rather than the planet, and it allowed them to pin down the precise temperature of column formation. They found that the hexagonal fractures form not long after the lava solidifies into rock, between about 890 and 840 degrees Celsius. That's around 100 degrees lower than the solidification temperature, and much warmer than what most scientists had assumed. Figuring out the conditions that create these columns is useful outside of the Giant's Causeway, because these columns are found all over the world. There's colonnades in Iceland, Portugal, Romania, Mexico, Greece, Vietnam, and America, among others, so knowing how they form gives us insights into the geology of each of these places. And these columns aren't even limited to our planet. They've been spotted in satellite images of a crater wall on Mars, revealing some of the red planet's fiery tectonic past. The columns aren't identical everywhere we find them, likely due to varying cooling rates and chemical differences. And researchers from China have shown that some fancy numerical modeling can help to simulate just how these columns are likely to form. That can be important if you're planning to build around your basalt, since it's useful to predict just how fractured the bedrock is. Not only that, but engineers can also apply the physics of lava fracturing to our quest for efficient, clean geothermal energy. In 2009, geothermal engineers were drilling deep into hot volcanic rock in Iceland when all of their cooling, lubricating fluid was suddenly and unexpectedly lost, draining away into the rock. But the 2018 experimental results revealed that hexagonal cracking can open up solid rock when it's still hot, increasing its permeability to heat and fluids up to 1 billion-fold. This helps to explain the engineers' fluid loss, but also offers engineers an opportunity in the future. Since geothermal energy relies on the release of heat from deep in the earth, these hot, fractured rocks could be targeted for more efficient geothermal boreholes. Of course, nobody's going to be drilling into the Giant's Causeway for geothermal power anytime soon. But this natural wonder, along with its hexagonal fellows across the solar system, is helping us to better understand our planet's history, as well as our own future. So while it may not be the result of some giant's love affair, it's still pretty special.